So the first thing we're going to do now is go over all the examples on all the problems on the exam. We can do that quickly. And then I'll start talking about the last lab, and that's the last topic for the class. And I want to remind everyone about the final exam and to state that the final exam looks like all of the exams that we've already had, with one exception. The final exam includes sorting. You'll need to know how to write out the sorting algorithm for the final exam, just like binary search. For exam 3, you needed to be able to write out the binary search algorithm. You'll need to know binary search for the final, but you'll also need to know how to write out a sorting routine. So other than that, when you see the final exam, it looks just like another exam. It's just got a few more problems added to it. And the problems will resemble the problems from exams 1 through 3. So you need to practice all of those. All right, let's take a look at this exam 3. And here's the problem, are identical. I think we've done this. I'll just do it again quickly. So the problem is to implement this function. We get two vectors A and B, and we need to return true if they're identical or false if they're not. And this is the Boolean value here. See that? That's the return value. So we know we need to return true or false. And if you read the statement here, it gives some information about what identical is. They have to be the same length, because if they're not the same length, you can't compare them, element by element. So that's the first thing we check. If A dot size is not equal to B dot size, then we return false. They're not equal. I always do that, don't I? Okay, so we take care of that business first. And then we need to check each pair of values, the first value in A with the first value in B, and so on. So we use a loop for that. And we could use B dot size or A dot size. They're both the same. We already checked that. And so if the value in A at I, if it's not equal to the value in B at I, then we know that they're not identical, and we return false. If we complete the loop and we don't return, that means every pair was equal. So then we can return true at that point. All right, that's that one. So here's a figure 2. It's a declaration of a function, min value. Like min value returns an int. That's the first fact we can make a note of. And it takes a vector of int. Actually, I see now I should have done this. It doesn't matter. It doesn't matter for the exam. But I should have written it like this, because min value does not modify v. So when we do const, vector reference, that means the function cannot modify v. The compiler enforces that restriction. So I should have put it like that, but I didn't. But it doesn't matter for the problem. All right, let's look. Provide an implementation of the min value function, whose declaration is shown in figure 2. The function takes a single argument, which is a vector of int. The function returns the smallest int that is in the vector. We need to find the smallest value in v. So we did something similar to this using a two-dimensional array. So we keep a record of what the smallest is. We have to set it to something. And because the vector could have all negative values, so we don't want to set it to 0. Because what if the vector has only negative values in it? Then we're going to end up with 0 at the end. So we're going to set it to something, anything that's in there. So v0 is the logical choice. And then we scan through v. We scan through V and we look for a new smallest value. So if V of I is less than smallest, then smallest equals V of I. And then we just return smallest. That's how we do it. We have to look at every item and then we need to keep a record. If we do it in our heads, we're keeping a mental record of it. It's the smallest thing we've seen. And we update that record as we go scan through the vector. We say, oh, I see something that's smaller. Well, now the new smallest value is 3, not 7. And then you keep looking forward. Oh, I found a new smallest value. Now it's 1, you see? So that mental record you're keeping in your head, that's like a variable here in the program, smallest. So we set smallest to the first value, and then when we find a value that's less than this smallest value that we have so far, then we adjust our variable. And I'm spelling this wrong. I'm going to leave it like that. All right, here's figure 3. Is lucky. So is lucky. Implement a function that determines if the vector contains at least one 7 and no 13s. The function returns true if the number 7 appears in the vector one or more times and the number 13 does not appear at all. Otherwise, it returns false. And then here's some examples. I think the mistake that this turned out to be the hardest problem on the exam. And I think one of the mistakes that people have made here is that they didn't test what they wrote with these examples. These examples are not comprehensive. One student wrote code that succeeded with all those examples, but it failed for this example. So the examples didn't present a comprehensive test, but these example vectors here were enough to debug everyone's code except for one student's implementation, in which this one would have been needed to discover the flaw. All right, so let's implement this. We have a vector v. We want to know if it's lucky. It has to have at least a 7 and no 13s. So I think the easiest solution that I saw, which was the most common, and I'll show that to you. The first thing to do, but it's not as efficient as the alternative solution. I'm going to show you the inefficient solution. So we scan the vector for a 13. If v of I is 13, then we know that it's not, it's lucky. It's not lucky. We return false. So the first thing we do is we look for a 13. If it has one 13, it's unlucky. So we just take care of that right from the beginning, and then we could forget about it. Now we want to make sure it has at least one 7. So we scan through it again, and if we find a 7, then we return true. And if we don't return true, that means there's no 7, so we return false. That was the solution that the majority of people wrote down. And there's other solutions. I'm not going to go over them. We covered that in the lecture, actually. See, it's 2 loops. We could do everything with a single loop. You keep a Boolean variable that tells you whether you found a 7 or not. So you check for 13 and 7. You find a 13, return false. If you find a 7, you set your Boolean variable to some state that indicates that you found a 7. And then when you exit that one single loop, you can check the Boolean variable to see whether you found a 7 or not. That would be the more efficient solution. All right. 4, write test code that tests every statement in the isLucky function in the previous problem. So we have a vector of int v. And we're going to push back a 7. You know what? I'm going to push back a 2. And we're going to assert that v is lucky. Oh, sorry, v is not lucky. So that test right there hits here. See? So we know we hit this one. That's where there's neither a 13 nor a 7. So we return false. So we hit the last line. And let's push back a 7. Now when we call isLucky, we're going to return true. So we're going to hit here. And it tests all of this logic, this loop, but it doesn't test this yet. It doesn't hit this statement yet, this substatement. So let's hit that substatement. Push back a 13. Now it's unlucky. So this last test triggers this logic right here. So that means we've covered everything. We have good coverage. We've executed every statement in the code. And keep track of this. You know, here v is empty here. When we push back 2, v is just 2. We push back 7, v is 2 and 7. When we push back 13, v is 2, 7, and 13. So that might help you to see what's going on too. All right, so that's that test. All right, 5, write a program that implements the guess the number game. And I pretty much told everybody to get this one ready for the quiz, for the exam at the end of our last lecture. I don't know if you remember that. But it's on record. It's on the video, so I know that I said that. So you just had to review this. And I like this problem because it's kind of like it's human binary search. You know, it's when you play this game, you're really doing binary search. So that's why I like it anyway. But here, this is how you do it. So it's this guess the number game. We've looked at this before. The key thing to keep in mind is you've got to keep asking the user over and over again to enter a number until they hit the one that you're looking for, 1776. So you need a loop. You have to repeat that over and over again. So we need something. We need some kind of loop condition here. So we have an n to declare. And then we check to see what n is. So we ask the user to enter a number. And look, we're doing that in a loop. So we're going to keep asking over and over again until they get 1776. So if n is less than 1776, then we're going to tell them it's too low. Else, if n is greater than 1776, then we're going to tell them it's too high. Otherwise, we found it. So now we want to exit the loop here. Yeah, you get your example up there. So there's a number of ways of doing it. We could just we could break here. That's one way to do it. But another way to do it, and I'll show that to you, is to check for n here. That while n is not equal to 1776, and several students use this solution. Now, for this to work, I mean, it's going to work normally, but you should initialize this n to some value that's not 1776, because you might run the program, and n, if n is not initialized, once in a million years, or less than that, you might actually get memory that has 1776 in it. So, but I didn't take off for that. But that would be a bug. So this is one way to do it. Any questions so far? I'm kind of zipping through these. And a lot of this is stuff we've already looked at. How about count negatives? So here's the function count negatives. Look, it returns an int. It shouldn't be having return true, or return false in your code. You should look at the function definition here, this function signature, and see that it returns an int. You have to return an integer value. And the function takes a single argument, a, which is a two-dimensional array of integers. Implement a function that counts the number of negative integers in a two-dimensional array with rows, and columns. The function takes a two-dimensional array of int and returns the number of negative numbers in it. A declaration of the function is shown in figure 4. The variables rows and columns are constants defined elsewhere in the program. You don't need to define them, just use them. All right, let's do this one. Count negatives. So we just have to count the negative numbers that are in there. So we're going to have, a loop. We'd have to have a nested loop. We're going to be looking at aij. If aij is negative, then we're going to increment some counter. And then when we're done, we're going to return the counter. Keep spelling that wrong. There we go. So loop on I, loop on j. So we need to cover all the I and j's so that we look at every element in A. So it's just translating this into code now. How do you express that aij is negative? Oops. Yeah, less than 0. So if aij is less than 0, we need a counter. We need to declare a counter and initialize it to 0. Counter. And how do we loop on I? Well, I'm just going to grab it up here. I should have just typed it out. So I is less than rows. Pose. and loop on J. So we start J at 0, increment J, so J starts at 0 and goes to calls -1. So that's how the code looks, counting the negative values. You're going to get something like that on the final, not exactly this problem, something like that, where you have to scan through a two-dimensional array and make a decision to do something like increment a counter or whatnot. And you see that you can check your work. You're returning counter, so you have to return an int here. It's just a mental check. You can say, yeah, am I doing the right thing? This is a little confirmation. If you notice that fact there, it just confirms that you're on the right track. All right, what about this one? Search. Implement a function that searches for a given value in a vector of integers. So here's search. Search returns an int, just like the last problem. And it has, the first argument is v, which is a vector of int. And the second argument is k. And notice we have const vector int reference. That means the function doesn't modify v. So that's just another piece of information that you could, to help you understand what you need to do. So implement a function that searches for a given value k in a vector of integers v. If the value is found, the function returns the index of the value in the vector. Otherwise, it returns -1. -1 means it's not there. Do not assume the values are in order. Therefore, you cannot use binary search. For example, if v is -2, 4, 18, 6, and if k were to be 18, it would have to return the position of 18 in v. See, -2 is at position 0, 4 is in position 1, and 18 is in position 2. So the function would return 2. So that's the example. I'll show you how to do that. And then there's another example. It'll return -1 if k is not in v. All right, let's do this one. So we need to scan across v and look at every value. So we have to look at v of I. If v of I turns out to be k, then we found it. We return I. Actually, most people got this problem. Otherwise, you return -1 after the loop is done. So this problem was, almost everybody got this one. So I think a lot of people get this one. All right, binary search. Implement binary search. I know at least one student derived the algorithm during the exam. That's excellent to be able to do that. And I don't see that you're here right now, but most people just memorized. There, you did it. Yeah, but most people memorized the code and then produced it. And that's good too. That's also a good way to do it. But it's hard to memorize every little detail. You really need to memorize the concept and maybe a trick or two. And that's enough, because then you can build the code from the concept and the memorization of one or two tricks. And then you build the code. But to memorize that, oh, there's a comma, then there's a plus, and there's a parenthesis, I mean, that's tough, right? That's memorizing a lot of little details. So I wouldn't recommend that. So anyway, let's do binary search. So we have a vector v. We have to return a position. So we're returning an int. So what we do is we have these bookends, we keep squeezing them in. So we have a start and an end. It defines a range, and we keep shrinking the range. We cut the range in half at each iteration of this loop. So we define a variable s to be the start position. That'll be 0, position 0. And then we have an end position, variable e, and that's v dot size minus 1. So we want e to point to the last value. We want it to be the position of the last value. That's v dot size minus 1. Because counting starts at 0, or labeling starts at 0. And then we have this loop, and with this condition here. And in the loop, we compute a midpoint. Start plus end divided by 2. And that does truncation. So if we got an even, if we have an odd number, then we divide by 2, then we're going to lose, the decimal value there. But that's okay. The algorithm still works. Once we compute the midpoint, we want to see the value at the midpoint. And we want to compare the value at the midpoint to k. So is k less than the value at the midpoint? If k is less than the value at the midpoint, that means the new end is going to be m minus 1. I'm sorry, the new end. It's going to be, we want to set it to the midpoint, but 1 before it, because we already looked at m. Else, if k is greater than the value at the midpoint m, then we want to bring up the start index. That'll be m plus 1. Else, we found it. We're going to return the index of k in v. Well, we found it. We found it at m. So we return m. And so when do we quit? When do we continue? Maybe that's a better question. We continue as long as, and maybe this is the trick you need to memorize. So we continue as long as the start index is less than or equal to the end index. As soon as the start is larger than the end index, we're done. We've looked at everything. All right. That's it. Any questions?
Turn negative.
Huh? Oh, yeah. -5 for me. I lose 5 points. Huh?
Plus 5 for all of us. Minus 5 for you.
Was that your problem?
Yeah.
Yeah, I took off 5 for that. Or maybe I didn't. I can't remember now. Yeah, so I'm a B student here, teaching you guys. All right, so that's it. All right, now application. This one. Tic-tac-toe. Now this is really the thing. This is really what we're culminating up to. Doing the problems that we've done so far is like learning the language and practicing things. Now we want to build a useful application. It's not that useful. It's going to be tic-tac-toe played at the command line. But it resembles something that might be a useful application. And once again, I want to remind everyone, there's lots of solutions on the internet. Don't submit a solution you found on the internet. You won't get any credit for it. You get no credit for getting a solution from the internet and submitting that as your work. If you can't solve the problem, or if you don't want to put the time into it, then you don't submit this lab. Okay? So just don't bother to submit code that you copied from the internet. You have to do your own work here. Otherwise, you'll get no learning out of it. If you look it up on the internet and solution, what kind of learning is that? I mean, you learned how to search for code on the internet. That's okay. That's not bad. But that's not the learning objective here. The learning objective here is to go through the process of software development, some process that I'm going to show you. and actually develop a complete program on your own. All right. So you need to write this program that plays tic-tac-toe. So I'm not going to show you how to develop that solution. I'm going to show you how to solve a related problem. And what I did for the last 2 quarters was I showed students, we went through the process in lecture, and we coded up a solution for Connect 4. Connect 4 is a game. Oops, I spelled it wrong. Connect 4 is a game. And what you do is you need to get 4 in a row. So we can get a diagonal. I'm trying to get this. Did I play there? Oh, I lost. Oh, you were going to warn me. Oh, yeah. I lost the game. Anyway, we did this. The last 2 lectures. So if I do this again for you now, I already have, I got it in my head how to do it. All right, so I can just like reproduce that. But what I illustrated, in the previous 2 lectures, especially the one before the last, when I did it for the first time, I was lost. I mean, I never solved a problem before. I just did it. And then we could work together and just sort of feeling, well, how do you go from a state of being lost, or not lost, but a state of, not having done something, and then how to solve it. And so what we could do instead of implementing this is I thought of another possibility, and I'm going to show that to you. There's another, it's like it's a puzzle. So it's like a puzzle game. Let me show you this. This is a mini game that was inside of a game called, what's it called? Machinarium? Machinarium. Does anyone know that game?
I know the one you're talking
Huh?
about. It's the one with the nuts and bolts. You have to
Yeah.
put a 4 on a large grid.
Not that one, but you know the game. Yeah, I'll show you. So they had a lot of mini games embedded in this bigger game. So you have something that looks like this. You've got these, say, O's and X's. And then there's a space here. So these are slots. And what you can do here is you can either move or hop. So the next thing that you would do here, you could maybe leave, this one would stay alone, this one would stay alone, this one would move down to here, and these would be the same. Oops, sorry. So this is the second state. So it's like taking this piece and moving it down. So you can move forward one. But see, now this X, we can't move it up because it's blocked. So we have a choice. This X can hop the 0 and go there. Or we can move this 0 forward to there. Do you remember this game? Yeah. I loved this little game. I loved all the little games they had in there. So, sorry, just messing that up. What do you want to do? Should we move the 0 down or hop the 0 with an X?
Move the 0.
Move the 0 down. Let's do that. So we move the 0 down. So, and now what do? We can't do it. The only thing we can do now is to move that 0 to there. You see that? Because this X can't hop 2. So we're stuck. Got it? Does everyone get that? So moving this 0 down isn't going to work. So we need to hop with this X. That's a better move. And now, for the next line, we can either move this 0 down, or move this x up?
Move the X up.
Huh? Move the x up? Okay. All right, we took your advice last time. So we're gonna see where that led to.
I was just moving it.
Move the x up, right? So that one goes there. So we move the x up. Now we can either move this x up or hop this x with the 0 and put it there.
Move the X up.
Move the x up?
No.
No, that is going to be blocked. But all right, so I think everyone agrees. So we want to hop, right? So we want to hop that one. All right, so we hopped that 0 right there, hopped the x, and landed there. Now, see, you can play the game. You play it to the end, all right? And you can do it. It's solvable. You get to the point where it looks like the following. So we started with the zeros on the top and the x's on the bottom, and we follow those rules, and we end up with the x's being on the top and the zeros on the bottom. It's solvable. You can get there. It's a nice little mini game, because you solve this and unlock something, and you go on to the next stuff. So that's your choice. Do you want to implement this, which I have never implemented? I don't know how to do it right now. Or do you want to implement Connect 4? And I already solved this one, so I have a pretty good memory of how to do it. Which one do you want to do?
Implement Connect 4.
Huh?
Implement Connect 4.
Connect 4? What's the other game? The mini game or Connect 4? How many people want to see the mini game? How many people want to see Connect 4? Wow, I think Connect 4 wins. That means that's easy for me. You guys don't mind that? Okay. Actually, Connect 4 is a little bit, it's closer to tic-tac-toe than the minigame. So in fall, I'll propose the minigame once again. I'll see how people vote. Yeah. But let's do Connect 4. All right. All right, Connect 4, as we solve this, you'll start to see how to solve the tic-tac-toe problem. All right? That's the purpose of doing this. And we're working at the console, so we don't have a graphical interface, so we don't have an interface like that. We're going to have to print the state of the board, we'll call it, over and over again, or the grid. Maybe we'll call it a grid. So let's start with a main program, and we'll get that from somewhere. Maybe lab 2, 3. We don't need CMath, but we'll need IOStream. All right, so we have a grid, and we're going to have a loop. We're going to have a loop here. And in the loop, we ask the user to make a move. What is your move? Think about it, what is it to make a move here? They choose a column. That's it, right? So we'll ask the user to choose a column. And then we're going to read in that column. And then we're going to do some calculations, and we're going to say, we're going to do, if the user wins, then you know, if the user wins, then whatever. And then the computer plays. And then if the computer wins, then whatever. So we have to have a loop that executes these things. And I'm just going to make this in pseudocode here. We ask the user to choose a column, input the column. Then we have to decide, well, did the user win? Actually, before that, we need to test if it's a tie. And if it's not a tie, then we're going to check to see if the user wins. And if the user doesn't win and it's not a tie, then we're going to let the computer play. And we're going to check for a tie again. And if it's not a tie, we check to see if the computer wins. If it does, then we terminate. But now after choosing a column, what we'll do is we're going to print, or we'll print the grid. I'm going to call it the grid. We're going to print the grid. And we're going to need to print the grid. I'm going to put the grid here. So we got a grid. It's going to be initially empty. We'll print the grid. And I'm going to put that in there. The void function. Print the grid. We print the grid. And then we prompt the user to choose a column. The user chooses a column. Then we print the grid again so we see the move. Then we let the computer play. And then maybe we want to print the grid there as well, right? After the computer plays, we want to print the computer's move so that you can see it. And then you check for a tie and check for a win. And just do this forever until you either have a tie or a win, and then you exit the loop. So that's just like the tic-tac-toe problem too. So you're going to ask the user to input a value, check for a tie, check for a win. If not, then have the computer make a choice. And then when you have the computer make a choice in tic-tac-toe, and we'll do the same thing here, is we'll have the computer make a random selection. So the computer will choose a random column in our case. In your case, the computer will choose a random empty cell in the tic-tac-toe board. That's too noisy, isn't it? That is way too noisy to have in the background. But now we have our first sort of prototype to test. So I coded it up so that this would run. Let's test it. Oh, column is undefined. So we'll make it an integer. I'm a grid. So we see the grid. Choose a column, 2. We print the grid. Then the computer makes a move. We print the grid, and we print the grid again. So we're printing the grid too many times. I think what we want to do is print the grid first, so it's empty. Then we ask the user for input. Print the grid so that we see what the user did. Then we can announce a tie or a win. Otherwise, the computer will play, and we'll print the, and we'll do this. We'll do cout. The computer plays. So test that. I'm a grid. So we see the empty grid, choose a column, 2. I'm a grid, we see our move, we didn't win, we didn't tie. Then the computer plays, we see the grid again. And now it's our move, the computer didn't win or tie, so we pick another column, print the grid, we don't win or lose, the computer plays, we see the new grid. So that works. By the way, I'm pressing Control C, because that's an infinite loop. There's no way to break that loop in code, so we just have to kill the program. All right, what about this grid? The grid. So the grid is going to be we have to represent the grid somehow, right? So we have blanks, we have blank spaces. Maybe we can use a dot for that. And then we have the player's move and the computer's move. So maybe an X and an O. And there are 6 rows and 7 columns. 6 rows and 7 columns. So we have 6 rows and 7 columns. You can think of two-dimensional matrix, two-dimensional array. And each position in that two-dimensional array will have a state. Either it's empty, or there's an X in it, or an O in it. So we have, and I'm going to use a char array. And there's 6 rows and 7 columns. We declare it there. I think, the new language definition, we would have to manually initialize everything. But I think we can just do this. I'm going to use a dot for an empty slot in the grid. I think that'll put a period in every position of this array grid. Let's test that. Well, we'll need to print that. So how do we print the grid? We have to print it a row at a time, right? So we got to change the columns. I'm going to use C for column. So, no. I have to do rows first. So we start with row 0, and while R is less than 6, we'll increment R. And then we do the same thing for a column variable. So for each row, we want to scan across the columns. So we'll use C for that. There are 7 columns. And then here we're going to print with C out. We're going to C out. I want to put a space in there. And we'll see out the character at the grid position RC. Now this data type, we haven't used this yet in the class, char. But that means a single character. And it's like a string, except you use these apostrophes, and you can only have one character in there. So it's like a string. It has the things you can store in a string, like characters and numbers, punctuation. You can store those things in a char. But you can only store one in a char, whereas a string, you can have multiple values. And so here, see, we're printing a single string, a string with a single space. We could have called that a char. It could have used the literal expression for a char like this. That's all right as well, but I'm going to make it look familiar. I'll leave it like that. We could have defined the grid as an array of string as well. That would have been all right. But this helps you learn a new data type. All right. By the way, when we finish each row, we need to have a new line. We don't need I'm a grid anymore, except it would be good to have a new line here. All right, let's take a look at that. Oh, we only get one dot, so it didn't work. This initialization doesn't work. So let's redo this. So we need to initialize that grid. And we'll do it like this. These two loops. So a grid of R, C equals dot. And now we have code there that initializes the grid. Kill the program. Choose a column 2. The computer plays. Choose a column 4. So now it seems to be working. So that's how to print the grid. Now you can imagine doing the same thing for tic-tac-toe, right? So you're going to have, you could print something that looks like a tic-tac-toe board. Now what we need to do is when the computer, then we just have to implement these pieces actually. Let me implement one piece here. Let's do the, when the user does a play here, when we choose a column, we need to, we're going to do something like this. I'm just going to, the thing is going to drop down. It's going to go into a column. It's going to drop down to the bottom. So the bottom row is row 5 because there's 6 rows. So 0 through 5. So put it into the column of row 5. So we'll have the user will be maybe X. The computer will be O. Let's see how that works. So 2, look at that. Choose a column, 5. See that? Now look, I entered in 2, see? I entered in 2, and this is position, this is column 0, column 1, column 2. So do we want the user to enter in values that start from 0 or start from 1? Start from 1, right? So let's do, so we'll take this, we'll just take 1 off that column, see that? Choose a column, 2. That looks like a column 2, right? That's we're building the program for humans, not programmers. Programmers are not human, right? Okay. So choose another column, column 1. Of course, they're not stacking yet, right? So I choose 2 again. I'm just overwriting that one that's there. Now we have to stack them. And so do you see what I'm doing? I'm building this incrementally. And I have a runnable prototype at each sort of step in this process. That's how it's done usually. It's not always how people say it should be done, but that's how I think most code in the real world is written. It's done incrementally and produced as a sequence of prototypes. Sometimes more planning goes up in advance, right? You got to do a lot of planning in advance. But this is a pretty small problem. But a lot of times the planning is not complete in the beginning. You've got to start prototyping just so that some of the issues start emerging. And then you start to know, oh, I need to ask these kind of questions. We have to have a planning meeting and work out some details, how the system is going to work. So it is incremental. And programs, when they're written, they're like living things. You know, it's like, suppose you have a video game that you're playing, right? Every once in a while, that thing is going to have to update because it's like a living thing. If bugs are found, you want to keep the user satisfied. If it's a kind of game like an MMO, that thing's always being changed all the time, right? So programs that are being used are almost always being updated. So they're like living things. So here we are, we're producing, we're growing this thing, a program, and we're doing it step by step. We're going to watch it grow. But that's all I'm going to do for today. We just have it printing the grid and accepting, a user choice. We don't have any stacking yet. But when we meet next time, we're going to continue with the problem. But this is enough for you to start on the tic-tac-toe problem. So you could figure out how to print the grid, how to get user input, how to display a character in the grid that the user picks. Forget about calculating whether it's a win or a tie or anything like that. Just get this far. If you can get this far in your tic-tac-toe program, that's great. And then I'll show you, how to do the rest of the connect problem, and then you can take it from there. Now, don't leave yet. Please don't leave yet, because I'm leaving early because I have what do you call it?
The teacher evaluation.
Yeah, teaching evaluation form there.
Can you scroll up before you exit that?
All right, scroll up before I do that. I'm going to post this online so you can see it. So just